welcome back. Today's background is kind of peak autumn from my travels in Japan. The background is Yamadera Station in Yamagata prefecture, which is a tiny walk down the road that way from probably my favorite temple in all of Japan, full stop. It's Hojuzan Rishaku Temple, and it's really nice because it's basically built into the side of this big mountain, and so you go in the bottom and the whole trip is basically just climbing up this mountain, going past shrine after shrine after shrine all the way to the top. And then up at the top you can see a whole pile of little wooden huts and stuff that monks used to sort of meditate in for long periods of time, just with this awesome view across the valley. It must have got pretty hardcore in winter though. It seems to get very cold because it's on the mountain range right when the sea comes in, so they get massive amounts of snow, and it's right near all the ski resorts. So if you're a monk who likes skiing, it would probably be the ideal place for you. Okay, so we just dealt with constraints, and what I want to do in this lecture is start out by defining a couple of terms, mostly because one, I will use them again later on, and two, if you go on to do a lot more mechanics, you'll see these terms come up again and again. And then at the end, I want to finish off by basically doing the final derivation of Lagrangian mechanics, which is to show that Lagrange's equations still work with forces of constraint. And as a byproduct of that, we actually just demonstrate that Lagrange's equations work without us having constrained forces as well. So it's kind of a catch-all derivation for everything in Lagrangian mechanics, which is why I really like it as a problem. Okay, so one thing we have to define at this point is degrees of freedom. So what we call our degrees of freedom, and you'll have seen me use this word in some of the earlier lectures as well, is the number of coordinates that can be independently varied in a small displacement. Okay, so we're really just talking about the number of ways that we can change our system mechanically. And so probably the best example here is our pendulum. If we go back to the one we just did, if we have a body that's basically can move in X, Y, and Z, here when we're attached to the end of our pendulum, there's really only one coordinate that we can change, which is just the angle relative to the pivot point of the top. Okay, and the reason why we care about the number of degrees of freedom is that if we have an n particle system, if there's less than 3n degrees of freedom, then the system is constrained, and then we have to worry about constraint forces. So if you sort of work through a checklist of how to deal with Lagrangian problems, usually you have degrees of freedom at the top, because what you want to work out is whether you've got less than 3n degrees of freedom. If you've got less than 3n degrees of freedom, you're going to have constraint forces, so you have to work out what's going on with those. You then work out what your final set of active coordinates is, and then you work through doing your Lagrangian approach from there. Okay, so remember this 1 degrees of freedom. It's a very important term. We'll talk about it numerous times. The what? What's with this?
Yeah.
Holodeck? No, I said holonomic. Come on. And Mad Pete Evans? Holistic? Really? Seriously? I don't know what we're going to work on with this. Okay, we got two terms here. Apologies for diagrams, training up a new trainee, and sometimes they're not listening very well. So there's two terms that we have to know for mechanics, and I usually hate introducing random nomenclature for mechanics or for any topic in physics, because it all just gets confusing. But these are two terms that are actually kind of important, and one of them we will come up against later. The other one is kind of a way of classifying problems that are sort of doable and not doable. So if we talk about natural set of coordinates, basically what we mean is a set of coordinates, generalized coordinates q1 through to qn, is natural if their relationship to the Cartesian coordinates does not involve time. And basically what that means physically is that for every point in time, your mapping of the coordinates in Q to the mappings of coordinates in X, Y, and Z remains the same. Okay, you can I'll let you try and imagine cases for yourself where that's not the case, where essentially your coordinate system in one is not the same as the coordinate system in the other, and so it depends on time how you map from one coordinate to another. Those are non-natural coordinates, okay? And later on we'll show where those become important. The other one is a system that's called holonomic, and a holonomic system is a system where the number of degrees of freedom is equal to the number of generalized coordinates needed to describe the system's configuration, okay? And possibly the best example of a holonomic system is the pendulum, right? The number of degrees of freedom is 1, and in order to fully describe that system, you need 1, okay? Sometimes the best way to make a term obvious is not to define the term, but to define the negation of the term. So if we want to consider a non-holonomic system, at first it might seem like that can't exist. Like, what are you talking about? You've got something where there's 1 degree of freedom. How can you need more coordinates than that? A nice example of this is the demonstration we have here. So let me let the video explain this one. The demonstration of non-holonomic system. So we have a triangular path here. It's got 2 sides of equal length at 90 degrees to each other. And what we do is we take a spherical object like this basketball and place it at the starting position on a corner of the triangle, and we do it in such a way that we know very precisely what the orientation of the ball is. Okay, so you'll notice that this cross is at the top with these 2 pointing along those directions. And so then we set this triangle up so that 2 of those sides are equal to the circumference. So we roll along one side by a circumference, and that will bring this position back to the top, same orientation. Then we go 1 circumference along the other direction, and of course that's going to bring us back to this at the top and same orientation. And then we go along the hypotenuse back to the starting position, being very careful not to slide or slip. So this is a pure rolling motion. And you'll notice when we get back to that starting position, the cross point's no longer at the top and the orientation has changed. And so in addition to x and y to describe where you are, you need some additional coordinates to describe the orientation of the ball as well. You can try that one for yourself at home. All you need is any ball you like. You can just put a little sticker with an arrow on it and work your way through the problem. And if you think about it, you've got an object. It's got 3 coordinates, x, y, and z. We have a constraint, okay, which is that it's sitting on a flat surface. So that knocks out 1. And so we're only dealing with x and y, which is fine. But we can't fully describe every detail of that system with just the 2 coordinates x and y in there, right? Because now we've got a rotation of the system and its orientation changes, right? If that ball was on that surface and it slid in that system, then we would have a holonomic system, right? There's 2 coordinates x and y, and they fully describe the motion of the system. As soon as you switch to rolling, there's a rotation implicit in that, and so you've only got 2 degrees of freedom. You can't rotate that object. You'll notice in the video I said you can't slip or you can't slide. So it's not free to rotate any way it wants. The rotation's tied to the degree of freedom of the motion because it's a rolling motion. But you need more coordinates to actually describe the state of the system than it has degrees of freedom, okay? Those systems end up being quite a bit harder because instead of having the nice thing of the Lagrangian approach, which is that your system reduces the number of equations, suddenly you have the number of equations go up to deal with that system, and often you either have to take some very clever approaches or you just have to work hard to get yourself out of it, okay? So beware of those. It's unlikely you're going to come up with problems like that in courses, but many of you will do mechanical problems later in your life, whether as working physicist or you're an engineer or something like that, and you need to spot those ones because they're the hard problems. Okay, one of the real skills in physics is actually spotting what are the simple problems and what are the hard problems, and sometimes the hard problems are worth either staying away from or being aware that you're in for a tough time. Okay, so there's one last thing I want to do today, which is basically to prove that do a proof of Lagrange's equations with constraints in place. Okay, and so this is essentially rounding everything out in terms of the theory of Lagrangian mechanics, so that for next lecture we can go through and just deal with examples and look at problems. Okay. And so what we're going to do here for completeness is prove that the action is really stationary. We're going to go back and sort out Hamilton's principle and not do it via the discretized approach that we did in lecture 3. We're going to do it with a calculus of variations, and we're going to include constraint forces in here because the limit of not having constraint forces just pops out of it quite neatly. Just turn a light on. Okay, so what we're going to do is deal with a particle moving on a flat surface, okay? In this particular case, it's the easiest way to do it, because we want a constraint force in the problem so that we can actually deal with constraint forces. And the easiest constraint force to handle is basically the rather annoying normal force that you get in first year mechanics. I don't know about everyone else, but it used to drive me crazy. It was the most painful force you could deal with. So you would have, you know, this mass sits down on this surface, and you need to work out what force it's subjected to, which is usually gravity, and then try and work out some imaginary force upwards that stops it from falling, okay? It's a constraint force. It constrains the motion from doing what it would normally do, which is to plonk, fall, okay? And we're going to have this thing able to just move in x and y directions, okay? It's not rolling, it's a mobile body on that surface, okay? So we've got 2 degrees of freedom. We've got an x direction and a y direction, and sometimes you see it DOF, and we're going to go straight to the most general approach here and call these Q1 and Q2, okay? And so you can imagine we would have some Cartesian coordinates here attached to them, x and y, but what we might want to think about instead would be like a radial thing and a phi thing, or we could just make Q1 and Q2 x and y even, okay? As a general rule, that's perfectly fine, okay? We've just got to make sure that we have 2 sets of coordinate systems that we can think about here in terms of this. Okay, so there's 2 coordinates, Q1, Q2, because there's 2 degrees of freedom. There's 2 types of force on the particle as well. The first one is forces of constraint. And in this particular case, it's the normal force. And there's also non-constraint forces. And so the non-constraint force is easy to see here. It might be just me giving this a push, and that means that the motion is just goes in that direction. Okay, so they're the non-constraint forces. They're the ones that act to give you a motion rather than act to constrain a motion in some direction. So in this particular case, it might be, for example, Coulomb's force, or it might be gravity, although gravity is a confusing one to consider in this case because we've actually constrained the motion in Z, so gravity doesn't really generate a motion here. But you can imagine if you had some other constraint, like our pendulum, for example. If you think back to the pendulum, you're constrained not to move in Z, then the non-constraint force here would actually be gravity because it's the thing that generates the motion, okay? So they're your 2 types. Your constraint forces are not necessarily conservative, and the one thing about Lagrangian mechanics that's nice is that we don't really care, and we don't really care because we never really see the constraint forces in this version of mechanics, okay? So we can kind of live with that, and we just work around them because we never see them. Some of you will be going, oh, that might be a pain, because what if you do want to know the constraint force? You want to know the tension in the string for a pendulum so you know how strong it has to be. There's actually a clever trick to do that. And we'll deal with that one in lecture 10. Okay, I'll show you how to get out your constraint forces for Lagrangian mechanics if you ever want them, right? But here we're going to assume we don't want them because it's the nicest particular case. So it's the non-constraint forces that we care about, and we can assume that those things are conservative, right? So we're going to have a net force in this problem, and we're going to basically assume that that comes from a potential, right? Because we can always do that. And so we're going to let that potential for the moment depend on both position, because you need that for conservative forces, and time as well is okay. And then we're going to have a total force on our particle. And let's call that F total. That's going to be our constraint force plus our net force. Okay, so it's going to be the force that generates the motion plus the force that makes that constraint to sit on a plane. Okay, same as you would do in first year. You combine, your force of motion with your constraint force and get a total force and solve your problems that way. Okay, and then we would have a Lagrangian, which is T minus U as we normally know it. And since the potential energy only comes from the non-constraint forces, the definition of L automatically excludes the constraint forces. Okay, this is why it happens. Okay. And we'll see later on when we come up with a method to get our constraint forces back. We actually have to add equations. We have to add things to get that constraint force to come back into the problem, okay? And it doesn't come in through that potential. All right, so we've defined enough things here. Let's get on with it. Let's consider, you remember we have to deal with this path problem, right? So we're going to consider 2 points. And they're going to be R1 and R2. And we'll assign them a vector because they're actually a position, right? And they're passed at T1 and T2, okay? And what we're going to do is we're going to call our correct path R of T, and it's a vector too, right? Actually, what it is it's an accumulation, so it's an integral of a whole pile of little vectors that represent the positions all the way along that correct path, okay? And so you're kind of used to this concept because we've done it for a couple of lectures now. All we're doing is just specifying a path, okay? And we can also specify a wrong path in here. And you'll remember the way we did this was we have our correct, let me draw it in a second. We're going to call this thing big R, just to follow the notation in Taylor, of T, okay? And also if you wanted to use W for wrong, you don't want to get confused with work. Okay, so let's keep this simple. You can imagine that we've got 2 points here, R1 and R2. And you've got some coordinate system that has an origin down here somewhere, so these would be vectors. You could draw a vector out to where they are. And you take some right path between the two, so this is how your R evolves as a function of time, between this being the case at time 1 and this being the case here at time 2, right? And you'll remember we dealt with this in the last lecture. You can take your wrong path, which is some other path nearby, be big R of T, and you can consider it to be a vector as well. Okay, so there's going to be some vector that starts from the origin here and works its way up to every single point on that path, and it can just be our original path vector, which would point along, let me change colors just so I can draw over the top. You can imagine our little path vector R at some particular point. We can add some vector to it, epsilon as a function of T, that would then give us our new R over the other side, okay? So we can basically write something a little like R of t equals R of t plus epsilon of t, okay? Where epsilon of t where epsilon of t is an infinitesimal vector pointing from little r to big R, okay? And so my drawing here is a little funny because I've actually drawn non-infinitesimal vector, right? You have to imagine it's very, very small. And so really what I'm doing is I'm taking one tiny little vector that points along this direction, and I'm taking an incorrect path by adding a little vector to it, right? So if we sort of did a blown up version of this, here would be the vector on my new path, here would be the vector on my old path, and then I'd have some little vector in here, okay? Just to make it clear that it's actually really a proper vector sum in here, okay? You may want to spend a little while just thinking your way around how that vector sum between the paths works just inside your head, okay? Mostly because in this diagram here, the first time you think about it, it's a little confusing, but if you think about it when you get down to infinitesimal limit, that vector sum actually makes some sense, okay? And the one thing that we require, again, is this endpoint constraint, okay? So we need R of t equals R of t at t1 and t2. And that endpoint constraint basically means that epsilon of t equals 0 at t1 and t2, okay? So we've got the same constraint we had in the last lecture. So we haven't really done very much at the moment that's different to the last lecture, aside from rename our paths and relate our paths via a vector sum, okay? So the logical step you have to take here is basically making that jump to the vector sum being the position rather than just arbitrarily labeling our paths. Okay, so we have an action integral. And it is the integral from t1, which is our starting position, to t2, which is our ending position, of L of big R dot, and t dt. Okay? If we're working on our wrong path, if we're working on our right path, it would be L of little r dot, and t. Okay? So it depends on what path we're on. But for the moment, what we're doing is we're trying to find the right path, which is little r, and we're assuming we don't know what it is, by working on wrong paths, big R, to get to it, okay? And what we need to do, or what we need to show here at least, is that we have to find a stationary to get that correct path, okay? So the aim here is to prove that A is stationary for variations in the path R of t when R of t becomes little r of t. In other words, when we hit the correct path, A must be stationary. Which is the same thing as saying when epsilon goes to 0. Okay, and we're specific about this because we could imagine that for very large epsilon, there's another stationary point somewhere out, and that's obviously going to be the wrong path. Okay, so we're going to want to work close to the path to solve this little problem here. Okay, and so another way to say this would be that we want delta, a thing we can call delta A, right? Which is the action for an incorrect path minus the action for the correct path to become 0 to first order in epsilon. And what this basically means is that if we move very slightly away, I mean, if you think about gradients, right? If we move very slightly away from the correct position, we want the action not to change. And that would be the case when the gradient is equal to 0, right? If the gradient wasn't equal to 0, we would get some finite change. So we're actually looking for a stationary point. And it could be a minimum where the gradient is 0, it can be a maximum where the gradient is 0, it can be an inflection point. But either way, a very infinitesimal move to first order in epsilon will give you 0 change, right? So that's what we're kind of looking for here. And the reason why we do this is that we're going to work not just on the action, but the action is an integral of Lagrangians. So we can basically make a thing here that we call delta L that is the Lagrangian for the wrong path, R dot and T, minus the Lagrangian for the correct path, R dot and T. And we know that L of R dot and T is going to be just T minus U, which is a half M R dot squared, okay, so X, Y, and Z coordinates built into 1, minus U of R and T, okay, and you can imagine writing a similar expression for big R as well, so it'd be a half M big R dot squared minus U of big R and T, okay. So let's do that. We've got delta L here is going to be our Lagrangian for big R. So let's write this down. It's going to be a half M big R dot squared minus U of big R and T minus the Lagrangian we have for little r. So it's a half M R dot squared minus U of R and T. And what we can do here now is write essentially this term up here as R is R plus epsilon, right? Just to clean up the notation and keep it nice and simple. So what we would have in here is a half M R dot plus E dot squared minus U of R plus epsilon and T minus a half M R dot squared minus U of R and T, right? And so now what we can do is just swap sides for the terms, right? Push all the potential terms over to the right, push all of the non-potential terms over to the left. And if we do this, you'll notice you can break it up yourselves and come back. The minus signs will work themselves out. So what we've got in here is a half M R dot plus epsilon squared minus R dot squared in the first side minus U of R minus epsilon and T minus U of R and T over on the right hand side here, okay? All right. At this point, we need to clean it up, and to clean it up, we need to pull a relationship from maths. I'm not going to derive it because it would take me half an hour, but you should basically know this one. It's that f for any function, for any scalar function f of r, that f of r plus epsilon minus f of r is equal to, or roughly equal to, epsilon times grad of f, right? This will be something you've done in your vector calculus classes. And so what we're going to do is use that to clean up this potential term on the line above into something we can work with as a vector calculus term, okay? And what we're also going to do is expand this guy out. So what we've got here is a half m r dot squared plus 2r dot e dot plus epsilon dot squared minus r dot squared. Okay, so that's the expansion there. And then this term on the right now is some scalar function u, and we know it's a scalar function, and we take the difference between it from two different points, we can get this. So really we just got to make substitutions here. So this will be epsilon dot grad of u. Okay, fairly straightforward switch over here. Now we can write this thing as something that looks a little bit like this. This r squared will kill that r squared. We've got a term in here that is really, we could see this as a dot product because r and epsilon we defined earlier as vectors, right? So it's actually a vector dot product. The two will cancel out the half, so this will be m r dot epsilon dot, okay? And this again is one of these skills in here. You can't put dots and vector signs and everything in here because it all goes crazy. Sometimes you've got to know what's going on by context, right? Minus epsilon dot grad u, okay? And I could put a vector sign on top of there if I want, but I kind of know what's going on, so it's not a big problem. And then I've got one term left over, which is this term here, right? And so what we're going to do here is just write order of epsilon squared. And the reason I'm going to do that is that I know that term must be tiny. And I know it must be tiny because I'm going into the infinitesimal limit where my wrong path is just off my correct path, right? So it's a really small contribution. And if I take a small number and I square it, I get an even smaller number, so I can probably ignore that thing, right? We do this all the time in physics. Get used to it now. We often don't care about very, very high precision accuracy such that we worry about really small terms. Often we just ignore them and know that we're going to be close enough to the answer. Mostly because you can never measure to infinite accuracy anyway, so a lot of these little terms don't really matter very much. Okay, so we're almost done on this. We can now jump back up to the action, right? And what we can write here is that our delta A, which is the thing we're interested in, is going to be just the integral from t2 to t1 of delta L dt, okay? I'll need to prove that one for yourself. That's pretty easy. You're basically just taking the difference between two integrals. This now is integral between t1 and t2 of m r dot epsilon dot minus epsilon grad u dt. Okay, so all we're doing is just pulling our expression that we got for delta L back up. And of course we can split this into two integrals here because the sum of the integral of a sum is the sum of integrals. So it's going to be the integral t2 t1 of m r dot epsilon dot dt minus integral of t2 t1 epsilon dot grad u dt. Okay. All right. At this point here, we're going to do a trick that we do time and time again in these sorts of problems, which is we're going to change the sign on this term on the front by using integration by parts. And I'm going to use a slightly different form for the integration by parts here. Okay, so what I'm going to use is integral of uv dash dx is equal to vu minus integral v dash u dx. Okay, and you're probably used to seeing this as integral u dv is vu minus v du. Okay, I'm going to let you prove this top one for yourself because it's actually really, really easy. You should be able to just go from one to the other basically by just introducing an extra variable that relates to x in order to get this thing. Okay, it's like 2 lines of algebra. So we're going to use this thing to deal with this first term up here. Let's call it a just to keep track of it. Okay, so we're going to come down here to a. And we're going to go integral t2 t1 of m r dot e dot, or epsilon dot, sorry, I'm going to call it e dot because I'm feeling lazy today, is now, if we use this expression above, it's going to be, we've got the definite part here, so this will be m, and of course I'm going to take my u here, and actually I've got something wrong over here. I've got these reversed, which I shouldn't have. It's u, oops, still not working. It's going to be u dash v just here, sorry. So it's going to be m, my u here is going to become u dash. So what I'm going to do is make my epsilon dot become an epsilon, and that means that my r dot is going to become an r double dot. So this will be r double dot dot epsilon between t1 and t2 minus integral t2 t1 of m r double dot dot epsilon dt in here, okay? And so you can see all I've done is I've taken r dot to make it r double dot, so it's the one that's is gone from u to u dash, and then my epsilon dot here becomes the integral of it, epsilon, which is basically my v dash going back to v, okay, on the other side. So that's all I've done in here, and then I've kept the extra coordinate dx to dt just to keep this thing right, okay? And they're both just integration by parts, it's just I have to introduce an extra variable to do it. I'll let you check that one for yourself. Okay, this term here is 0, and it's 0 because epsilon of t1 is equal to epsilon of t2 is equal to 0, okay? And so you'll see in this in the earlier lecture, we do it time and again. In these sorts of problems, we use integration by parts and we rely on the endpoints being where the correct path meets the wrong path so that the epsilon goes to 0 just at those 2 points, okay? So that first term is 0, and what I'm left with here is minus t2 t1 m r double dot dot epsilon dt, okay? And so again we end up with this nice idea here that if you're working with a path where the endpoints join up so that your definite term in the middle here goes to 0, you can basically take a product inside, differentiate one term, integrate the other, and just put a minus sign out the front, okay? And you get used to this after a while doing lots of mechanics problems as just a viable route to solving problems in this version of mechanics. Okay, so that means now our delta A here becomes, where is it? Up there. Now we're fixing up our term A, so this is minus T2, T1, M, R double dot, epsilon dt, minus integral T2, T1, epsilon dot grad U dt in here, okay? All right, we did this to get a minus sign in the end, but also to get an epsilon that we can pull out the front, okay? So we can turn this back into one single integral here, which is now integral from t2 to t1 of mr double dot dot epsilon plus epsilon dot grad U dt. And of course we can pull the epsilon out, so this is now t2, t1, epsilon dot mr double dot plus grad U dt, okay? And of course you know that vector dot products are commutable. You can reverse the terms and it makes no difference to the two terms. All right, we're now pretty much at the end of the game here. So we know that R of t is the right path. And therefore it satisfies Newton's law, right? Satisfy Newton's second law. Basically just Hamilton's principle there. And so what we can say here is that mr double dot is going to be equal to the total force. And of course, that is our constraint force plus our non-constraint force, as we defined it earlier. But we know in here that grad u also is going to be equal to minus our net or non-constraint force, okay? And so now we can take one last step in our term down here, oops, stay still, delta A. And it is to do this, minus T2, T1, epsilon dot, we can put into here our mr double dot, right? And so it's going to be fc plus f. And then we add our grad u, right? Now grad u is minus f, so this will be minus f just here. And of course this, dt. And of course this f cancels this f, they're the same thing. And so this thing reduces to minus integral t2, t1, whoops, make that a 1. Epsilon dot fc. And of course these two things are vectors, dt. And this is our end result here for at this point. Okay, so if we want delta A to be 0, in other words, we want our action integral to be stationary, we require this thing in here to be 0. There's two ways it can happen. One is we have no constraint forces, in which case we automatically get this thing to work, right? And we've already shown that kind of twice. We did it in lecture 3 very explicitly. And if you take lecture 2 where we do it for a path using calculus of variations and just swap the path for the action, you know that's the case, and there we had no constraint forces too, and it automatically ends up as 0, okay? So that's one way to do it. We just take fc equals 0. If we have constraint forces, this term in here is not immediately obviously 0 because epsilon is heading to 0 but it's infinitesimal, right? And fc is not 0 because there's a constraint force. But the interesting thing to think about here is your constraint force is always going to be perpendicular to the plane of constrained motion, right? So if you think about our constraint force as the normal force here, our plane of constrained motion is the xy plane, and our normal force points out of it, right? And the reason why you require that is because if the constraint force had any component in that plane, it would actually generate a motion, right? And it would no longer be purely a constraint force because it would be a non-constraint force as it generates motion, right? So the only way you can have that is, or have a constraint force that doesn't generate motion, is to have it perpendicular to the plane of the constraint. But the other thing that we know is that we defined the right path and its adjacent wrong path to be inside that plane because we have to be able to move along the wrong path, and if the wrong path goes out of the plane, it breaks the constraint, right? And the vector epsilon will point from a point on the correct path to a point on the incorrect path, so it must implicitly be in the plane, right? So we've got a dot product between epsilon, a vector that must be in the plane, and fc, which must be a vector perpendicular to the plane. And so we know that epsilon and fc must be perpendicular to each other, and so that dot product has to be 0, okay? So E dot fc is always equal to 0, and so this thing above in here is always equal to 0, okay? And so now we've just done something really nice, which is to basically come up with a derivation that proves that Lagrangian mechanics works and Hamilton's principle works, not just for the case where we have no constraints, but also for the case where we have constraint forces, right? Because we know that constraint force has to be acting perpendicular to the plane of constraint to knock out that particular coordinate, okay? So the other way to see it here is to get rid of z, you have to constrain to the plane perpendicular to z, and the force follows correspondingly from that point, okay? It's a really nice place to stop. We've now basically derived everything we need to do basic Lagrangian mechanics problems. And so in the next lecture, what we'll do is do a bunch of problems, stepping our way from easy ones to much harder ones, and just basically spend a whole hour doing problems. I'll see you next time.